Let's work another sample problem. This one's also out of chapter 12, number 72. In this problem we're considering a solution that's made from naphthalene. It's an organic compound. Has a formula weight 128.17. This is its formula C10H8. We dissolve that in hexane. This is its formula, and its molar mass is about 86.18 grams per mole. We make the solution such that the concentration of the naphthalene is 12.35% by mass, and we want to know what is the vapor pressure of the hexane above the solution at 25 degrees Celsius. I underline that because the problem specifically asks for the vapor pressure of the hexane above the solution, not the naphthalene. Okay, so we're just interested in the vapor pressure of the hexane here. It's important to note. Got to read these questions carefully because sometimes they're pretty tricky. Okay. Specifies 25 degrees Celsius, and we know that P0 for hexane at 25 Celsius is 151. This, of course, is the vapor pressure of the pure hexane, okay, without any solute dissolved. So, to help us solve this problem, of course, ultimately the direction that we want to go is to use a quantitative relationship that looks like this. We know this from that Raoult's law business, that the vapor pressure of our hexane above a solution that contains hexane with something else can be solved as the mole fraction of the component of interest that's volatile. Here that's hexane times P0, where the P0 is the vapor pressure of the pure substance. Now, of course, we're happy about having the P0 given to us in the problem. It's 151 torr. So that one's almost a freebie. But nowhere in the problem do we see the mole fraction of hexane. So we're going to have to solve for that. Okay, we need to know what that number is, and as soon as we do, we can solve this problem and easily get the vapor pressure. Now, if we review the information that we're given in the problem, it's an interesting problem because we're not told much about the solution except the mass concentration of the naphthalene in the mixture is 12.35%. Now, in the problem itself, if you read the book, it'll tell you the mass concentration is this, or it's 12.35% by mass. I've chosen to write M/M here, which is basically an abbreviation for mass percent. So if you see that, that's what's meant by it. Now, how do we go from a mass percent to a mole fraction? Okay, we're going to think about that a little bit. The way I'd like to approach this is sometimes done a lot in chemistry, is to assume that we've got a solution of this stuff in hexane, and the entire solution is 100 grams of mass, okay? So the 100 grams is both the naphthalene and the solvent, the hexane, okay? Now, if that's the case, by the definition of mass percent, okay, and the fact that it's 12.35% by mass, in that 100 gram solution, I would know that I would have 12.35 grams of my naphthalene, C10H8. And I would also have the remaining balance. That would be my solvent. That would be my hexane, okay? You do the math on that. You have 87.65 grams of hexane. So what I've done is I just assumed 100 grams of the solution, and from that, and the mass percentage, figured out how many grams of each component that would have. It's okay to assume more or less any starting mass that you want. I just chose 100 grams because it's convenient. You know, it's a percentage out of 100, so it's easy to come up with these numbers. You could have chosen 1,000, could have chosen 10,000 or 50. It doesn't matter. You'll end up with the same answer. And the reason why that is because the mole fraction is not dependent on the amount of the solution that we assume. Okay, so for any starting amount, the mole fraction will end up being the same. Now the grams will be different of each component, but the mole fraction of both components will remain identical. Okay, so it's safe to assume any value you want. Assuming a starting amount makes it easy to kind of project how much will be present. Okay, so I've just chosen 100 grams out of convenience. All right, now the beauty of that is now I've got masses to work with. And of course I can convert masses to moles pretty easily if I like to. So I'm going to do that down here in the corner of the board. I'm going to take my 12.35 grams of my naphthalene. And I'm going to multiply that by my conversion factor. That relates 1 moles to grams of naphthalene specifically. And it looks like the formula weight, which is 128.1705. Will do that for me. My gram units will cancel because this is grams of naphthalene, and I'll get moles. So if I do the math on that and do my 12.35 divided by the molar mass, I end up with 0.09635 mole of my C10H8, my naphthalene. Okay? Going to need to do the same type of calculation for my hexane. I'm going to erase this up here because I'd like to keep these calculations kind of apart from this work over here, which I'm going to do later, okay? So, organize things a little bit. Now, if I'm going to compute my moles of the hexane, the solvent, I have to start with the realization that in my originally assumed 100 grams, I had 87.65 grams of my hexane. Do the same kind of calculation. I divide by the molar mass, or multiply by the conversion factor, which would be 1 mole over the molar mass in gram units. For my hexane, C6H14, my formula weight is 86.18 grams per mole. So if I do the math on that to find my moles of hexane, I quickly realize that I've got a little over 1 mole, 1.017 moles of hexane. So now I know the ingredients in my assumed 100 grams. A little over a mole of the solvent, hexane, and a little under 1/10 of a mole of my solute, my naphthalene. Of course, the beauty of all this now is now that I've converted to moles, I can find my mole fraction. And if I know my mole fraction, boy, I'm in business because I can multiply that by my P0 term that was given in the problem, and I'm done with this business, right? So let's compute the mole fraction of hexane, our volatile solvent. Looks like we've got 1 mole of it, or I'm sorry, 1.017 mole of the hexane present in the mixture. And remember, mole fraction is simply the number of moles of the material in question divided by the total number of moles of all components. So I still need to write that number down here in the denominator, because that's the mole of the one component, but I've also got a secondary component, and that's, of course, my naphthalene here. So 0.099635 moles of that material, okay? I dropped my mole units here, so don't lose sight of that, okay? I'm just taking some shortcuts here in the mathematics, okay? With the mole units, we can cancel out and end up with a mole, quantity that's unit-free. It's just mole fraction, okay? And that's, of course, the mole fraction of a hexane. And I'm going to multiply that by my 151 torr, which was my P0 term. That was the vapor pressure of the hexane by itself with nothing dissolved. And if I work out the math on that, I get a vapor pressure of 137.93 torr. So straight off my calculator, right? 137.93. And if I think a little bit about sig figs, it looks like this would be a starting point that's got 4. However, it looks like we've only got 3 for our P0, so I might want to truncate my answer to 3 as a result. 3 sig figs, if I was doing that, I'd have to basically have this be my last digit, so this is 137.93. I'm going to round up 138 and call it a day. So the vapor pressure of the hexane above this mixture is 138. It's a pretty easy example for how you could demonstrate this vapor pressure lowering business, this Raoult's law business that we talked about in class. The hardest part about it was getting to the mole fraction. And of course, you can do that if you understand the definition of mass percent. You can basically, and the trick to doing that was we had to assume that 100 gram volume, okay? Which is a pretty typical thing. Sometimes you have to do that. And of course, you have to come to the realization that the mole fraction will be the same regardless if you have 100 grams of material or if you have 1,000 grams of material or even a million, okay? So that's how you work this example problem.